Hello and welcome in this nicely dry shelter. We will now witness a presentation by Non Sequitur and A-Band about hardware hacking for software geeks. Basically on which end to grab your soldering iron when reverse engineering embedded devices. Have fun.
Hello.
Before we start, I'm going to have to make a request that you hold questions until the question and answer period, because our monitor is unplugged so that we could plug in some stuff up here, and it makes it hard to hear things coming from the audience.
All right, our talk is hardware hacking for software geeks. The purpose of this talk is to help people who have written applications but maybe haven't worked much with hardware to know where to start. I mean, you have a device, you may not, or you know what it does, but you may not be able to interoperate with it, or you want to change how it operates. And this is a starting point. So we're going to go over how to set up a lab, how to design your own embedded devices, and then how to reverse engineer someone else's embedded devices, because those things are all interrelated. If you don't know how devices are designed, there's no way you're going to be able to reverse engineer anything without knowing the common design patterns that embedded devices share. So,
I have a lab in my home, and I found it immensely useful for aiding my work because it provides a space where I can, when I'm in that space, I know that I'm there to hack. It's not my bedroom or my kitchen or a space that I use for other things. Initially, I had about a 12-foot by 12-foot room, but I've since moved and now have 15 by 20 feet, and that's for one individual. Most of it's given over to storage. It's in a basement, so I've had to add an exhaust fan for ventilation. Good ventilation is key if you're working with hobby electronics a lot, because soldering, etching circuit boards, sanding the edges of circuit boards even, release chemicals that you probably don't want to inhale. A particularly bad example is the etching process, which tends to release either chlorine or very pure oxygen, depending on what process you're using, which is very hard on your lungs. You want the area to be well lit so that you can see what you're doing. Brighter light will cause your pupils to become small, which actually does help your focus. You generally want work lighting, which is to say the light needs to be located above the work, not in the center of the room, so that the light is cast on what you're working on and not the back of your head.
another important thing is grounding and ESD. That's a term that if you ever are in a commercial hardware lab, ESD is a big deal because it means electrostatic discharge, and it can very subtly damage an electronic board, and it most likely it's not going to fail immediately. It will not work in a way which won't appear for months possibly, but it will be broken and cause the device not to operate properly. I mean, it's going to appear to be working, but there's a lot of things you can do to prevent this from happening. And the reason you do this is so you have control, and you eliminate one extra variable. So when it doesn't work, you know it's your fault, not the board's. And you can get grounding mats and the wrist bracelets that you ground yourself so you don't shock the board and take out a component. And another thing, if you have pets, you want to get an ESD coat, because the material of the coat prevents a static charge from forming on the hair from the pets, and then if the hair touches the board, it won't shock the board either. So if you have lots of cats or a dog that's long-haired, ESD code is probably a good idea if you want to work with sensitive modern electronics.
If you're going to be doing any hardware modifications, you probably ought to learn to use a soldering iron. How many people here have any experience with soldering? Okay, a good number. I don't want to talk down to people too much, but for the people who haven't had any experience in it, how many of those people know what it is? Okay. Soldering is the process of attaching electronic components or other metal pieces together using a molten metal, usually an alloy of tin and lead, although recently the ROSE directives have forbid the use of lead in a lot of consumer electronics. The tool for soldering is a soldering iron, which is basically a piece of metal that's heated electronically to melt the solder. The solder is just essentially looks like a very soft metal wire, but it contains a core of a flux, which is a material that when it burns in the heat of the soldering iron, cleans off the parts that are being soldered together with a caustic vapor. This vapor is another reason to have ventilation in your lab. If you inhale it for very long, it causes headaches, dizziness, and a variety of other unpleasant symptoms.
You also want to select the right solder. I've destroyed a couple boards because when I first started off, I didn't have anyone there to teach me, and I got a solder which was too thick of a gauge and an iron that didn't have a fine enough tip, and I was globbing solder all over the place, and when I tried to fix it, traces would come up, and I learned the hard way that you want to get the stuff that says electronic solder. It's a very fine gauge, and maybe a 20-watt tip for soldering and a 40-watt iron for desoldering connections. Another tool which is useful is a desoldering wick or bulb for removing solder, either from your own work or to free up a port that's been closed through wave soldering when they were attaching the PCB assembly to the PCB board.
Another point of solder selection is the metal composition. The most common is 60% tin and 40% lead, I believe. I may have the numbers backwards, but it's marked as 60-40 solder. The lead is, of course, lead and is poisonous. But it makes the solder much, or at least I find it easier to work with. If you don't want lead, there are lead-free solders available. Usually they'll have somewhere around 2 to 5% silver in them as well. It makes a slightly harder solder, and I don't find that it wets as well, which is to say it doesn't seem to bond as well to the parts, but it is lead-free, and so you don't have to take typical lead handling precautions. That's not good.
No, it's not.
We have a little problem with the slides. Modern electronics packages can be very difficult to solder. There are packages such as ball grid array packages, which consist of, instead of pins coming out of the side of the component, an array of very small solder dots all over the bottom of the component. When the component is resting on the board, there's no tool that can reach under it to solder those points, so they have to be soldered by some other method. Generally, that's heat applied via either radiant heat from an oven or directed hot air from a hot air gun. These are some techniques for doing it in your home. In a commercial setting, they would usually use a hot air oven or a soldering oven, which has a computer-controlled temperature settings and usually costs $2,000 and up. Obviously, for the home hobbyist just getting into this, that's not practical. Toaster oven reflow soldering uses a typical toaster oven like you would find in your home. The Viennese camp, I believe, was actually using one of these to solder controller boards for a LED display that they're making. Essentially, the part is held down using a paste that is the solder dust, like as a metallic dust, combined with a liquid flux. That's applied very carefully to the places where the solder is needed. the part is set in that paste, and then the entire assembly is baked. As the temperature rises, the flux burns away, which results in the parts being cleaned by the flux vapor, and then the solder itself melts. The surface tension of the solder is sometimes sufficient to align the parts precisely, but generally you want to be as precise as possible when placing them. There are kits available to build temperature controllers for toaster ovens, and the kits are very inexpensive, less than $50 American. Another technique is to use an electric skillet. It's the same general idea, applying a gradually rising heat to the board. But in this case, the top is open, so the ventilation is easier, and you can watch the progress of the soldering. You'd never want to do this and then immediately cook your breakfast on the skillet. Like I said, dangerous chemicals everywhere. Hot air tools can be used both for soldering down electronic components and for removing them. I recently had an opportunity to do this in the Hack Center when removing a 25-pin connector that had half of its pins soldered down. Since there was no way to heat all of them at once using a normal iron, we borrowed a hot air tool. This is a homemade hot air tool. What basically happens is air is pumped through the handle and then through this heating element. The air then hits whatever part is being heated and eventually melts all the solder joints in the hot air blast. This can be used to desolder entire microchips at once, which is very convenient if you're salvaging from deceased pieces of electronics. And is also useful if you find out that you've made a mistake and don't want to desolder 30-some pins by hand.
Other tools are a good multimeter, which has a volt ohm meter on it. Analog or a digital oscilloscope, which can read signals, and a logic probe or a collection of logic probes, which is known as a digital logic analyzer. Now, those can either be home built, or you can purchase cheaper USB versions online, or if you were to be working in a commercial lab, the same equipment can cost anywhere from $5,000 to $50,000 and up. For the good high bandwidth equipment for doing work with modern general purpose processors. But for our purposes, we're not going to be working with anything over 40 megahertz today. So something with 50 megahertz of bandwidth is more than sufficient.
A commercial logic analyzer, can everyone hear me?
You got to get your mic closer.
Back a little bit.
Nope.
Hello? Okay. A commercial logic analyzer is typically a PC running a full-fledged operating system with specialized data acquisition hardware on it. I have one at home that doesn't quite work yet, but it's about the size of that suitcase and brand new, cost around $10,000, I think. Obviously, I didn't buy it for that price, or I wouldn't have been able to afford to come here. A volt ohm meter is one of these devices. It basically just displays voltage, current, resistance. This one also has a diode check function, which can tell you if a diode is blown or not.
Well, multimeters also can have things like frequency analysis. If you've got a pulse width modulated signal, you can put it into a frequency analysis mode, and it'll give you the hertz or the frequency of that signal. And there's lots of functions that they can put into the more advanced ones.
Some of them also have capacitance and inductance measurements. There are some that have a thermocouple that you can hook up to it to measure temperature. All these features, of course, add to the cost. This one, mine, is fairly basic, has lasted a good number of years, and has some features I don't even use, like a serial port in the top end for connecting to a computer.
We've already sort of covered this for a bit, but I have a oscilloscope here, which it's pocket-sized and uses the laptop instead of being a dedicated device, so it's known as a virtual instrument. Now, it may not have the same bandwidth as this, but it has a programmable open source API. Oh, it's not open source, but it's a freely available API, which you can develop your own virtual instruments and basically use it however you want. So it's fairly nifty, even though it's yeah.
The logic probes display the state of a single digital logic line, where an oscilloscope would displays voltage over time. This merely tells you if the voltage is high or low at any given instant. They're very simple to build. I was giving away kits in the Hack Center a day or so ago. If you already understand how one works, you may be too advanced a student to go ahead and build one, so I ended up buying mine. But if you want to get into digital electronics, building one of these is a very good first project. A logic analyzer is like having a whole bunch of oscilloscope or a whole bunch of logic probes all together. This model is displaying a whole bunch of traces here, and it displays with time in that direction and logical state in that direction. Generally, they're multi-channel. The better the model is, the more channels it will usually have. You can build a very simple one that will hook up to the parallel port of a PC and use Linux open source software, which only does 8 channels, but at sufficient bandwidth to do things like debugging the SPI inter-chip communication protocol. I'm going to try something and see if I can't be tricky enough to show you all what this looks like. And maybe... perhaps not so much. The software I'm using is called the Fabulous Logic Analyzer. There are several programs like it, both for Windows and for Linux. I have put links to them in the Hardware Lab section of the wiki if anybody wants to go check it out. The hardware required to use this software is very, very simple. It's maybe $10 American worth of parts and can be put together in an afternoon. The downside of having this cheap hardware and free software is that the performance is not exceptional. On the parallel port, the software claims it can sample 1 million times per second, which means it's only good for about a 500 kilohertz signal. Anything faster than that will start to display aliasing, where if there was a dip in the signal, it might be missed, and between 2 samples, the software will interpolate that there was no dip in the signal.
Another thing to take note of is some of the new USB devices are actually mixed signal. They're not oscilloscopes and they're not logic analyzers, but they're both. And the value of this is it puts both signals in the same time base. And for some smaller electronics, that can be useful if you're doing frequency analysis of a, let's say, some sort of radio transceiver, and also probing pins on the other side of that chip. It can be really useful in reverse engineering some of the protocols.
Especially in mixed state devices, anything that has both analog and digital components. This particular model may not have the bandwidth to deal with something extremely fast like the GNU software radio peripheral, but something slightly slower, less powerful, it may be able to deal with quite easily. This is another USB tool called the USB with lots of E's. It does logic analysis, oscilloscope, protocol analyzer for serial protocols and inter-IC communication protocols for between individual chips on a circuit board. The problem is it costs 1,500 American dollars. You get an entire lab for that, but it's still a fairly pricey device, and it only works on Windows. There are some do-it-yourself tools available. I am somewhat slanted towards Linux tools because I run Linux on my laptops and my desktops. Xoscope is a program that allows you to display, to treat your oscilloscope or your sound card input as the data source for an oscilloscope. It has some problems with bandwidth primarily. The bandwidth of an oscilloscope is how fast or how frequently or how high frequency a signal it can handle. The sound card of a typical computer is designed for signals in the audio range, so outside of that range it may not be very effective. We're hopefully going to be able to get a screenshot of Xoscope here. I don't have anything hooked up to the sound card, so it's not displaying anything useful, but basically This axis is time, this axis is voltage, and it supports multiple channels. There are stereo inputs to sound cards, so obviously there's 2 channels right there. Some sound cards have multiple stereo inputs, so you can get multiple, like 4 or more channels. It usually requires some buffer hardware to protect the port against accidentally plugging it into something that's of higher voltage than the port can handle. This is a buffer that I built at home. Hold on, can I bring that back up?
Yep.
Let's see here. Those are the inputs. They're BNC coaxial connectors, like would be used for a typical oscilloscope. And then the outputs from here and here go to the sound card and have trimmers on them to adjust the level. The other potential issue with using a sound card as an oscilloscope is that it tends to be AC coupled. That is, the signal is passed through a capacitor before getting to the rest of the electronics, which can be a problem if you're watching a DC signal because it tends to cause rounding on the edges of the signal. The parallel port logic analyzer I already mentioned. JTAG wigglers and flash dumpers I'll be covering a little bit later.
There's many sources for cheap tools, especially whether like power tools. Harbor Freight has Dremels for $5 almost. USD, they're all made in China. They're not going to last as long as a brand name tool. But when you're building your first lab, you can't really spring to have everything at the best quality, or else you're really going to be hurting for money afterwards. Also, you can try eBay. You may find some good deals on there. A lot of things might be marked as is, but who knows?
One good example that somebody pointed out to me at camp here is a device called the Logic Dart, I believe. I'm looking at my notes as we speak. It's a 3-channel logic analyzer in a handheld unit with a digital display. And it supports recording, zooming in and out on the signal, triggering on certain changes in the state of the wires that you're watching, and is conveniently pocket-sized. He said it comes up for around 150 euros, usually, I believe, 2 or 3 times a year. One will come up on eBay. It looked like a fantastic tool. It also supported most of the basic functions of a volt-ohm meter, so it was essentially a small hobbyist's lab in a handheld unit about that big.
Another good place.
I'm not certain that hamfests are as common in Europe as they are in America. Does anybody know what I mean by hamfest? Okay, I see 2 people in the back. A hamfest is a get-together of people who are amateur radio operators. And it's much like this, only they're more into radio and less into computers. Generally, they have a sales section, a vendor section, where people will try to get rid of their old equipment and buy new equipment. This stuff's usually used. Some of it's very weird, but it's generally it's an interesting place to get interesting bargains. So we have a question in the back. He's stating what hamfests are called. What was the word again? Oh, radio rallies. Okay, that sounds very similar thing, different word for it. Dumpster diving is, of course, the art of pulling old things that nobody wants anymore out of their garbage. This is actually how I got my oscilloscope, which is an HP unit with 100 megahertz bandwidth, so it's sufficient for simple microcontroller projects, but a little too slow for modern computers. Also, if you know anybody who works at a college that has an electronics lab, that can come in extremely handy. Colleges have a higher budget than the average hobbyist, and if you know somebody who works in the lab, they may be able to get you in and let you use the equipment for a few minutes. This came in very handy when I was reverse engineering the serial protocol of a magnetic card reader. Autodidacticism, sorry about the spitting, is teaching yourself. These are a couple of authors. Forrest Mims wrote books for Radio Shack, which is an American corporation similar to Conrad Electronics, only perhaps nowadays not as much focused on the hobby market. His books are compendiums of electronic circuits. So if you're looking to do a specific task, those are very useful. They're all available through Amazon.com. Just a quick search for his name will turn them up.
Another great reference book is The Art of Electronics. Now, this book has been around since before I was born. It's recently been updated, I think, within the last 5 years. And basically, it goes through from simple circuit analysis all the way through every type of component imaginable you'll find on a board, and explains exactly what it does and how you design for it. So if you're building your own robotics projects or reverse engineering a board and you look up a part and you're like, this chip is an optocoupler. What the hell does an optocoupler do? You go in the back, you look up optocouplers, and then you'll find 5 sections which explain different uses for that part.
The Art of Electronics is structured as a textbook, so if you feel like teaching yourself all of electronics, you can start with basically high school math and eventually end up being, if not an RF engineer, then able to pass as one in common society.
The other nice thing is it's very light on the math. It's not going to get you an engineering degree if you master the material in the book, but it will give you a very practical knowledge set of, it's basically where the rubber meets the road. So it's all very practical and down-to-earth type explanations of how everything's done and how to make real circuits, not theoretical ones.
Application notes are produced by the manufacturers of generally semiconductor components, but almost all components have some sort of application notes attached to them. It's basically a description of how to use the part in a circuit, which can be very useful if you want to design something simple with a core around 1 or 2 chips that you can get application notes for. Maxim Semiconductor is especially good about their application notes and gives very verbose examples containing how to do all sorts of very useful things with their ICs. Generally, they will, the producers of the chips will give the application notes away for free as a way of promoting the use of their ICs over those of their competitors.
They're not always called application notes. Like with the Motorola and Freescale processors, you'll find a user's manual. And for an IC, that means it's a very detailed description of every memory mapped register, every pin, every possible configuration of that chip and maybe other chips in its family, how to access the memory, the timing characteristics of the buses. It's, they usually are about 500 to 600 pages long, but it's a PDF, so it's not like you have to print it. Now, embedded engineering is our next big section. I'm not sure what happened to this slide, but basically, wow. So when you're starting your own, it's not reverse engineering, but
forward engineering.
Yeah. So when you're starting a project, you've got to look at what your requirements are. And let me skip. When you're gathering requirements, some of your requirements may be cost, it may be the space, size, weight of your device. Like the weather balloon is obviously a weight-sensitive electronic device if you're hooking up to that. Things like a badge for a convention, that's going to be very cost-sensitive if you're mass-producing it. And other things, what is the basic needs that the device needs to meet? So does it need to route? Does it need to transmit wirelessly? And is it a real-time application? Does it, are there lives depending on it? If it misses deadlines for control circuitry of like an airplane, if you you've got various certifications and hoops you've got to jump through. So those are important design decisions that have to be made early on.
This process is very similar to the software process in that you gather the requirements for the project, figure out what's available. In software, it's libraries. In hardware, it's ICs or sub-assemblies that you have already completed. Design it, put it together, test and refine, sometimes an iterative process. If you see a circuit board that says rev and then has a number other than 0 on it, they've redesigned that one at least once. Usually they'll have prototype revision numbers before they actually get to a release, because nobody wants to open something up and find out that it's the 100th design that they went through before they got one that worked.
Now, after they've got the hardware assembled, there's hardware and software integration, and then testing and refining the design. When you're selecting your chips, the architecture is fairly important. Do you need...
There, I'll take this over.
Do you need fixed point arithmetic? Do you need floating point? How fast does it need to be able to compute? How much memory do you need to store your application? Is it going to be need a lot of RAM, or just because some of these micros only have 2K of RAM, and others can have up to a meg of RAM depending on your chip selections, and whether you want to go with off-board RAM and flash to extend that. And that also, the cost requirement would factor into that. I/O, what sort of communication protocols do you need? Are you going to be talking to other off-chip I/O devices via SPI bus or I2C, or are you going to have a serial or AirInc or whatever? So that also determines what chip you select. A lot of the embedded chip these days have a system-on-a-chip architecture. Now, the way that works is they have a CPU core, which is the core which every chip in that processor family will use. And each processor in the family shares the same instruction set. Now, in addition to that core, they'll have like a unified bus which connects all the on-chip peripherals. And that's not so important from a software side, but they'll have multiple like CAN modules or RS-232 or SPI or PWM for doing pulse width modulated signals, or parallel ports, lots of GPIOs. So you've got to figure out what your I/O requirements are from your microprocessor when you're selecting a chip.
All these peripherals are built into the chip, and so the lower end members of the family will have the same core but may not have the same peripherals. For example, where a high-end member of the family might have 16 data lines in 2 ports of 8 bits each, pulse width modulation for analog output, and a real-time clock with a watchdog timer so that if the code crashes, the chip can be reset. But a lower-end member of the family might drop one of the ports and perhaps have fewer counters or lose the watchdog functionality. It just means that they won't be putting those on the silicon, and they'll sell the chip for less money. But it will still be able to run the same code as long as the code doesn't depend on having the resources of the better members of the family.
Out of the embedded architectures that you have to choose from, PowerPC is generally going to be a 32-bit architecture, as well as ARM, I think, comes in 16 and 32-bit variants.
ARM comes in a whole bunch of flavors and
yeah.
is very common. It originally, I believe, was in the BBC Archimedes computer way back in the day, but nowadays is used as an embedded chip. There are versions of Linux that target ARM, and it's usually used basically anything that's very high power but not quite requiring the full power of an entire PC.
Actually, it would be low power requirements, but high computational throughput.
I should clarify. Power in terms of computational power, not energy consumption.
But the other unique thing about an ARM architecture is ARM is the only one that the people who draw out the ARM specifications don't actually manufacture any chips. So you'll find that you'll have a wide variety of ARM chips all manufactured by different people, because the people who develop the specifications don't manufacture them themselves. x86 is not really that common in embedded applications unless you're throwing a whole lot of computing power at it. It's usually overkill for just about anything you'd want to do.
Sometimes shows up in factory controllers, though. The PC104 architecture is a specification for a very small type of embedded board. It's a full computer about the size of a sandwich. They're available in x86 as well as PowerPC, ARM, variety of other architectures. The last two architectures on here, PIC and AVR, are kind of very low-level microcontrollers. I have a few in here. They're very simple hobbyist-level controllers. These ones, they're
The
16...
HC9S08 also falls into that because that's another 8-bit chip. The register width is another factor because they still make 4-bit chips for very simple applications. I mean, that's like what a CD player will use with a DSP chip, and the code will be mostly assembly, but very compact and very low
power consumption.
Yeah.
These chips have 16 megs of, no, 16K, excuse me, whole different order of magnitude, of on-chip flash and a 16 megahertz clock speed. They cost about $4 each, which is interesting when you consider that 20 years ago, within living memory, the computational power that I'm holding in my hand would have taken up this room and cost thousands of dollars, and also made it too hot for all of us to be here.
Another thing to note is all of these chips use a system-on-a-chip architecture, and if you're not using a specific peripheral, you can use the memory-mapped registers to turn it off and use its pins as GPIOs. And some of the older PICs only have GPIO ports, so it'll be separated into like a port A, B, and C, where A will be the addresses, and then B and C will be combined into data lines for accessing and executing instructions from off-chip storage. Now, when you're designing your own project, you can usually start looking for evaluation or prototype boards. And they can be as cheap as $20 to $50 or as much as $500 to several $1,000s. And basically what that gives you is a chip, a crystal, a power supply that's well engineered, and breakout connectors for every pin on the chip. And usually a prototyping space like a solderless or soldered breadboard, so you can start building things on there without having to do much groundwork. So for a software person like me, it's very easy to stick a couple LEDs in the breadboard or maybe a Ethernet chip and connect up the SPI bus and build up the connector for the RJ45 and see if it'll work. Some of the prototyping boards have RJ45 already on there, a couple serial ports. It's a very diverse market, but that's where you'd start so that you can start developing software while your more hardware-inclined friend would be developing the hardware with you, or you're learning how to design your own hardware to manufacture.
The one downside of the development boards is that they tend to have the highest end member of that chip family on them to give you the full experience, as it were, with all the ports, all the on-chip peripherals, all the things that family can possibly do. When you move to a production environment, then you end up with you may end up with a restricted version of that chip for cost reasons. So it's good to keep the eventual target in mind when doing the development. For a hobbyist, that's not as big a deal because hobbyists tend to prefer a chip that they can buy in single quantities. And if you can buy a chip, the highest level chip in single quantities, it may not be that expensive, and so the evaluation board may be sufficient, and using all the abilities of that chip may not be a problem later on.
The next thing that may influence your chip selection is your tool chain. There's free proprietary tool chains available like MetroWorks, which this speaker badge uses. Or you can use GNU tools to build your own cross-compiler for whatever platform you're on to whatever platform you're on, if that version of GCC can actually build a cross-compiler without errors on your platform. It's usually such a pain to build your own cross-compiler and libc that once you do get one, you immediately put your binaries into source control and freeze it for the entirety of your development unless you have a very, very good reason to change it.
When we gave this talk at DEF CON, I was approached after the talk by a gentleman who develops for NetBSD, who said that the NetBSD ports collection cross-compilers may be considerably easier to use than the Linux ones. I don't have any experience in that area as I'm a Linux user, not a NetBSD user, but considering that NetBSD has been ported to basically anything capable of running computer code, I tend to believe him.
Yeah, I mostly work with proprietary tool chains because that's what my employer forces me to do. I've been trying to, preach the wisdom of using
spread the word.
Free tool chains that will always be available. Because if your proprietary tool vendor decides, oh, we don't want to upgrade this to Vista, and then Microsoft says, well, we're not going to support XP anymore, and your specific tool that you've been using for a device which has been in the field for 15 years no longer is able to work on a system which is secure, assuming XP was secure, then you're SOL because all of a sudden you don't have a tool that will work on your operating system. Additionally, another thing is licensing. Sometimes the company will go out of business and their licenses will be on internal timers, and if they're not around to renew it, you're also out of luck.
Another point is that as a hobbyist, you may not want to be constantly changing what architecture you use, and therefore will want to pick something that has a good future ahead of it. This can be a problem if the company decides to end of life that chip or family and end support for its compiler as well, because your part may become increasingly difficult to get. The compiler may be lost due to a hard drive crash or whatever, and then you will have to pick up a whole new architecture.
The next decision you have to make is going to be what structure your software needs to have. Is it adequate to do a simple while loop that's going to start at the top, go straight down, and execute each task, maybe the same task a couple times to have it execute more frequently than other tasks in that loop and then start over at the top? And that's what's known as a bare boards app, because there's no scheduler, there's no operating system, there's no drivers or anything except for what you write yourself. Or you could have a while loop which does round robin based on timers, or some more sophisticated things would be like a real-time OS. Now, what a real-time OS's purpose is to schedule to meet deadlines, and there's a couple types of deadlines. You might have soft deadlines or hard deadlines, depending on your application. As I mentioned before, in avionics, if you have to complete a task every 5 milliseconds to update a display, which, let's say, a traffic collision avoidance system, and you miss those deadlines, and you're displaying stale data, you can see how that might be a problem. Having old data on the display, so you think the plane is here, but really it's here, can cause a lot of things. So the way you get around this is with a real-time OS. And what that will do is it'll preemptively schedule. So it'll stop whatever it's working on and to meet specific deadlines that are critical. So it schedules tasks based on priorities, distance from deadlines, and things of that nature. It all depends on what your needs are for that. You can also use embedded Linux. Routers will typically use embedded Linux or VxWorks.
Embedded real-time operating systems aren't just for aircraft control. They're also useful in applications that are timing sensitive, such as home-built CNC machines. There's a kind of a community online of people who are building computer-controlled machines for building other things. That is, say, routers that are controlled by computers or saws that are controlled by computers in order to machine pieces of material. Those tend to use a real-time OS because it's important that the moving components only go as far as is necessary, and that the computer always have a consistent model of the location of the workpiece and the material being worked on. DOS has sometimes been used as something like a real-time OS, and it sort of is in the sense that the application is the primary thing running, They're still interrupts, but the Sisters of Mercy, the band, used a DOS box as their drummer for years and years, so he apparently had at least that level of precision.
A free real-time operating system available. There's actually two of them. I don't have them both listed on this slide, but one is FreeRTOS. I cannot vouch for the quality of this project. I was just digging around online and found it. And another one I've seen cited in some books I've read is eCOS. It's lowercase e COS, and that's used as a learning example quite frequently. Now, if you do go the bare boards route, when you're developing your own drivers for the system on a chip architecture, if it's an interrupt-driven device, so you need to have a finer degree of control than just pulling it every once in a while. It usually means you're going to separate your driver into 3 parts. You're going to have an interrupt handler, which responds to interrupts like received byte of data to free up the data receive register and move it into a queue somewhere and then return to where it was in the program. You're going to have a low-level layer, which is going to have buffers and queues and have an application interface to that, and then you're going to have your application logic on top of that, which is going to decide what messages to put into those queues and how to parse the messages it receives. Now, I just kind of went through that.
Well, another option is not having an OS. On the smaller chips that I was waving around, there's no space for it and there's no need for it. It's very simple to access everything directly, so you don't need the hardware abstraction that an operating system provides, and there's nowhere to put it. The flash is just too small. Generally, a chip that's running software with no operating system works by having the the reset interrupt start running the code that you have put on the chip immediately. So the chip powers up. When it powers up, the reset interrupt is called, and the reset interrupt handler does whatever initialization is required and then jumps to the beginning of the code. For those chips, they actually have a bootloader as well, which is a piece of code that allows reprogramming the chip on the fly. So you reset the chip. The bootloader waits for a message to come in telling it that it's going to be reprogrammed and then sending reprogramming data. If it receives that message within a certain amount of time, it'll write the new program into its flash memory and then jump to the beginning of that program.
The advantages to using a bootloader is it allows you to reprogram your device without having to open it up or possibly connect up a JTAG cable or a BDM cable and program it directly. You can do it via Ethernet, you can do it via serial or CAN bus or whatever communications bus you want, and usually the chip manufacturer provides some free assembly code which you can use however you want and modify however you want to put software into the application area of the memory. Now, when you start dealing with more complex projects, you're going to find that it makes sense to use more than one microcontroller. So you might have one 32-bit microcontroller that interacts with 5 smaller 8-bit microcontrollers, each of which connects to a peripheral device, like an actual mechanical device like a pump or a fan or some stepper motors, and needs its own logic, but it doesn't make sense to have all that logic in the larger chip, and some of that's for power reasons, some of that's for space and processing constraints. But the same object-oriented practices that you use in software design, you can also use with hardware design. So you might have several microcontrollers on a board, each connected to different pieces of equipment that are off-board.
Another example of object-oriented hardware is RF modules. RF engineering can get fairly complicated, as any RF engineers in the audience can probably tell you. But there are modules that have solved this problem. They're basically a small piece of circuit board that you can just plug into your board and supply with power, ground, and a digital signal, and they turn it into radio, send it some radio signal, send it out, and another receiving unit turns it right back into a clean digital signal. I found this immensely useful for a project I was working on that required remote control, because I didn't have to basically learn how to build a radio. I could just take this module, add it to the project, and essentially it's like a library. If you want to decode MP3s, people have already written libraries to do that. There's no reason for you to unless you really want to learn to decode MP3s. In this case, I didn't have time to learn all the RF engineering I would have needed to build this module, and so I could just use one that was already built for me.
Now, there's a couple communication buses that you can use. The CAN bus is typically used in auto or avionics applications, and is very common on microcontrollers because of the wide industrial uses for it. So a CAN bus may connect your ECU of your car to a smart pedal, which is no longer it's no longer a mechanical push-pull cable, but it'll have its own microprocessor that's going to send a signal that has the position of your gas pedal and then translate that into a throttle command that it sends to the ECU controlling your car's engine. Now, they've got CAN protocol decoders that are built into digital logic analyzers and things so that you can decode CAN messages. You can buy PCI MCIA cards that have CAN buses on them, and basically it's inter-device communications when it's not used on the same board. SPI, which is known as a three-wire bus, is used between chips. Two-wire or I2C is also used between chips.
These protocols allow you to communicate with another IC that has a complicated functionality without having to use a whole lot of lines. A good example is temperature sensor ICs that support an I2C interface. The temperature sensor could be returning a 10-bit number that represents, say, the temperature above or below a certain set point or whatever. But you don't want to dedicate 10 full lines just for transferring the data, plus another line for telling it that you want it to transfer the data, plus your power, your ground, and the other signal that it might accept. So this bus allows you to have a two or three or four wire serial protocol between the chips, where one chip will tell another one what kind of configuration to go into or what sort of information it wants, and then the other one will send back the information serially, which saves a lot of time saves a lot of circuit board traces, less wires connecting everything. RS-232 is also showing up more places than a 20-year-old protocol has any right to be showing up.
It's also used on the PCB to talk between multiple microcontrollers. So if you've only got two microcontrollers on the board, it'll be common to have an RS-232 channel between them, because at that point it's just two wires. You've got an RX line, a TX line, and it's not being shifted out to a port, but it may be useful to take that into account to see how to sniff the line.
It's a well-known protocol, and so it's very commonly implemented on chip. It's not uncommon to find an IC that has dedicated circuitry on it for doing RS-232 transmission and reception, just because it's easy to implement and everybody knows how it works already.
Other inputs to these microcontrollers are analog to digital inputs, which they translate a voltage value between 0 and 5 volts to either an 8-bit or a 10-bit value from 0 to either 255 or 1023, and then you multiply that by the proper divisor to turn that into, you multiply the 0 to 1024 to get your voltage value. And then based on what's connected to it, whether it be a thermistor, an RTD sensor for temperature, or pressure sensors or whatever, that's going to allow you to translate that voltage value into a actual value, whether it be in foot-pounds or however you measure that here.
PSI, degrees Fahrenheit or Celsius, depending on which side of the ocean you're on.
Another source of inputs are there's also high-speed inputs, which are capture devices. These can measure frequencies of signals. So if you've got, say, a tack sensor that's measuring the speed of a shaft, that's going to come in. It's going to have a 1 for each time a dot on a gear goes past the sensor. And so it's going to create a PWM signal based on the shaft speed. So it's going to go up when it's across the dot and then back down again. And then the frequency of that will tell you how fast something's spinning. So for things where you're measuring speed, you might need a high-speed input. Or for controlling something, you might use a PWM output. And that is a pulse width modulated signal, which means you've got a period, and a duty cycle. The duty cycle is how much of the period is actually at the 1 logic state and how much is at the 0 logic state. Because you could have a 1 millisecond period, but be at 1 for 1 microsecond or 999 microseconds.
Reverse engineering is becoming a more and more complicated legal topic all the time. In the United States, we have the DMCA, which is intended to prevent the distribution of circumvention devices for getting around copyrights, but is frequently used in what's called a SLAP suit, or a strategic lawsuit against public participation, to attempt to prevent someone releasing a tool that may or may not be used for circumventing somebody else's copyright. US law is a local ordinance, but as we've no doubt found out, the laws are getting more and more restrictive everywhere. Reverse engineering shouldn't, in my opinion, be illegal, and I suspect that that's a commonly shared opinion, because it allows people to recover lost functionality of their hardware. A common example is the
Hacking tools?
well, yes. Yeah. But also there was a television recorder that had the ability to automatically skip commercials. They were sued off the market. The only way to get that functionality in a television recorder now is to build it yourself or add it to one that doesn't already have it, such as the more recent generation TiVos. Essentially, laws like this are damage, and they will be routed around, not only because people want their devices to do more, but in the name of simple capitalism. It's not the guy in the basement that the governments should be worrying about. It's the guy in the manufacturing plant in China who has found out that they can sell more units if they have more functionality in the unit. And so if the US can't manufacture a unit with commercial skip, or Germany can't manufacture a unit that might be used as a hacker tool, then they can manufacture it there, sell it, and now guess where the money goes? The process of reverse engineering hardware is very similar to that of software. You start with something that is a finished product, probably from someone else, probably that you didn't have design input into, and you have to figure out how it works and which parts of it are parts of interest to you for modification. You generally first break it down into subsystems, figure out what the parts of those subsystems are and what they're doing, and then figure out which ones you need to change to get the functionality that you want. In software, you would be opening something up, figuring out the various functions, and then figuring out which ones, say, do things like locking your MP3s so that you can't use them anymore, and replacing that with something that, say, immediately returns 0. In hardware, this could be looking for a line that is trying to determine whether or not a certain operation is permitted, and wiring it to high voltage or low voltage, depending on which one means go ahead and do it.
That could be involved in re-enabling the write line on a TSOP or flash chip, because sometimes they'll cut the trace for the write line to the on-chip memory, or not on-chip, but a memory chip that's also on the board, and by rewiring that you can enable yourself to be able to load whatever firmware you want into the device. And using the engineering process, you can, knowing the specifications of the chips, the interconnects, what pins are wired to what, you can arbitrarily create your own firmware if you know how all the chips on the board work and how they're connected.
I say the changes are optional because you don't necessarily have to be opening things up and learning about them to modify them. You could just simply be curious. That's how I got started in electronics, opening things up, figuring what does what, just because I wanted to know how things worked. And if, as an outgrowth of that, I happen to be able to repair things or improve them, then so much the better. Printed circuit boards, or PCBs, are the base part of any circuit. I have one here. This is the DEF CON speaker badge. And it shows actually some interesting examples of how to read a printed circuit board. This one doesn't have a silk screen, which is an interesting... Oh, good plan. This one does not have a silk screen. This one does. If you look closely, you'll see that there's white writing all over the board. That writing indicates what type of part each one of the parts on this board is. So resistors are marked with things like R6 or R5, where R means it's a resistor, and then the number means is just to make the identifier unique for when they're talking about the board in the plant. This is useful because there are some parts that are so small. If you look closely, there are some here, like those little tiny things right there. Some of those are resistors, some of them are capacitors, some of them are even microchips, like these little black things. And without the silk screen, it's hard to know if they're transistors, microchips, or what. Another useful thing about this is that sometimes they will print what missing functionality is on the board. I have a router at home that has holes in it and a sign that says USB 1, where there could have been a USB connector, but there isn't. So in theory, I could figure out what parts were needed to make the USB work and then add my own USB connector to the device.
Now, this router in particular has the RAM on the back of the board here, but it has empty pads on the front of the board here and here. And if you're capable of adding your own RAM chips, it's a very difficult hack, but you could expand the RAM on this from 8 megabytes to 16 megabytes and double your capacity of what custom applications you may want to run on it after reflashing it.
Another aspect of reading circuit boards is to look at the traces, which are the very fine wires built onto the board via usually a chemical etching process. Generally, thick traces means it's carrying a lot of power, so that's usually coming from the power supply circuitry. If you're not interested in modifying the power supply, it's good to know where it is so you know what not to look at. Thin traces generally are carrying signals and are made thin just to make the board tighter, to put everything closer together.
Another thing about power supplies is when you're dealing with consumer electronics and your board has a lot of peripherals, your power supply that came with that board may not be able to handle the amperage to drive all of those all at the same time. Because in the cost-cutting process and board revisions, they may reduce the cost of components and decide, well, we're never going to be using all of it at the same time, so we can design it so that it's impossible, and you can actually damage your equipment if you were to write firmware that did that.
One of the probably last but by no means least is what the parts are and what they do. Generally, most places leave the parts with their manufacturer labels. Sometimes they sandpaper them off to try to prevent reverse engineering. If the labels are on the chips, Google or octopart.com will usually help you find data sheets for the individual parts, which explain what the signals coming out of the part are, how it reacts to various temperature changes, its current consumption, all sorts of basic information about the chip. The problem with this, though, is that some manufacturers do not release their data sheets unless you've signed an NDA, or they don't release them, period. Generally, the smaller manufacturers do this because the bigger manufacturers would sue them. Companies like IBM or Intel maintain enormous patent collections, whereas smaller companies will try to go trade secret rather than maintaining patents. At least this is the case in the US. I'm not sure how it works elsewhere in the world, but I suspect that there are similar rules regarding I'm informed that the rules are very similar. That if you build a chip that replicates the functionality of another chip too closely, you could be liable for intellectual property violations. To prevent the bigger companies finding out that they've duplicated their functionality, the smaller companies simply don't tell anyone how anything works. That can be a problem if you're a hobbyist looking to get this information, because they don't want to deal with you, that is to say, give you an NDA, assign somebody to work with you, that sort of thing, because you're maybe going to buy 3 of their parts. You're not doing a production run the way a major corporation would. It's useful to be able to recognize common subsystems. One thing that if you look at this, could you get the camera up here? If you look at this board, you see some fairly large components over in one corner. In fact, you can probably see these without the camera. Generally, large components are your power supply. Big capacitors, big inductors. Let me pull them up here. That right there is an inductor, and this one and that one are capacitors, and they're large because they have to be. They're handling all the power for the entire device. That one is just large because it has most of the silicon in this device is on that chip. That controls all the routing, does everything else that the chip does. The wireless chip is this one over here. The way that I actually recognize that one of these is wireless and the other one is the routing chip
Here, why don't I hold this up and you point on
makes sense.
the screen?
Okay, that's a good plan. The way that you recognize that this is doing all the routing and this one is doing all the wireless stuff is that this one has traces, and you can't quite see them right here, but they're basically very fine wires going over here. And then over here, there's an inductor that goes right to the ports. So we know that this is mostly doing the routing. This has around it this copper area. On some version of this board, there's probably a shield that solders down to that for noise suppression, but this is the lower end of this router. I'm informed that if you get the high-end version, there actually is metal shielding over this, and that's just for noise suppression. The way you can figure out that this is for shielding is that that entire copper trace is all grounded, so it's to provide a solid metal shell around the thing. We can tell that this is power for a couple of reasons. First of all, there's the big components that I mentioned. If you look up some of these ICs, you'll find out that they're power regulation components. And of course, the dead giveaway is that this blob over here is the power connector. That's where it came into the board, and the traces just go straight through this area before going out into the rest of the chip, or the rest of the circuit. Whoops. Back one.
Oh, another thing to look at are the physical characteristics of the device, because that's also going to drive your design. Your basic requirements are the chips on the board, how much RAM you have, the speed of your processor. If you've got a 4-bit processor, obviously, and only a few bytes of RAM space, you're going to be programming in assembly. Some smaller micros don't even have RAM; they just have registers. And if you only have a handful of registers to work with, the only thing that you can use is assembly. And for real-time devices that do this, they'll actually count the number of cycles per assembly instruction to get the timing right. So that's when then they'll inject no ops, and it'll just be one long infinite loop. If you've got a couple megabytes of ROM and flash on the board, then you might have a real-time OS or a very, very large bareboard application. Bareboard applications can typically fit in under a meg of space and use anywhere from 2K to 512K of RAM very comfortably.
If you have a device and you don't know how it's communicating with other stuff, then you're probably going to need to end up reverse engineering a protocol. The most basic case is if you already have a device that speaks that protocol, and then you have the ability to basically snoop on a session. This is really useful, especially with serial communications, where they'll use a standard RS-232 for the link, and then we'll send some sort of, basically they'll pick a certain set of symbols that they want to send back and forth to indicate, do this, do that, this is the status, this is what you should do about it. And you need to know that in order to, for example, write a driver for an operating system that's not supported by the manufacturer. If you don't have something that already speaks the protocol, such as a computer that's already running the driver hardware, then fuzzing may be useful, it may not. It depends on how well the software on the device is written to handle unusual events. Because if you start throwing random data at it, it may crash or it may behave strangely. If it does either of those things, it could harm the hardware, or it could just be that you'll gain no useful information. Crashed hardware is not as easy to debug as a computer because there won't generally be an error message, it just stops. One thing that works in our favor, though, is human factors. Protocols are designed by people. When they're designing and building these things, they want to be able to debug them easily. I purchased a magnetic card reader recently, a reader and writer, rather, that communicated over the serial bus. But I didn't know what kind of communication it was, what data was sent back and forth. and I didn't have the software that I would need to run it on a Windows system and then snoop that transaction. So I needed to figure out another way to get the data out, or to get the protocol out of it. So I pulled the ROM out of it, which was a socketed chip that just stored all of the software that was used to run the thing, read it, and then reverse engineered that using typical software reverse engineering tools. It turns out that the read command is the letter R, the write command is the letter W, reset is Z, which is familiar to anybody who has used an AT-compatible modem as the reset carrier for that, reset signal for that type of modem. In other words, the protocol was designed so that a person developing the software for this device or developing the device itself would have an easier time understanding it themselves. And as a consequence, anybody coming into it later would also be able to understand it easier.
Other tools are, well, BDM, depending on which configuration. BDM is in no way, shape, or form a standard. Some BDM ports are one-wire interfaces into the chip. Some are 2, 3. It really depends on what microcontroller specifically that it's connected to. You can have 6-pin BDM connectors or 8-pin as far as the pin header goes. But from the ones I've worked with, you can't dump the ROM via BDM. So if it does have a BDM port, which is mostly Freescale and Motorola chips, then there's no way to get it off using a BDM reader. JTAG, on the other hand, is...
well, BDM, have you gone over the acronym?
That's a background debug mode, and it's just a generic term that they use for debug pins on the chip. And usually you need a proprietary pod to talk with it, which is usually via USB. Sometimes it'll be parallel port or even serial based.
JTAG is another on-chip debugging methodology. It stands for Joint Test Application Group, and it's I believe 4 wires in the core of the bus that are used to send signals to the chips on a board to do things like modify registers, determine the outputs or the states of the pins on all of the chips, intercept signals between chips, read and write flash memory, which is very useful if you're loading your own firmware. It generally does not support things like single-stepping an application or modifying code while it's running. There are enhanced versions of JTAG, like MIPS eJTAG, that support that sort of functionality, but until very recently, those were not standards. They were individual manufacturer extensions to the protocol. There is some Linux support for MIPS eJTAG, but until very recently, it was entirely reverse engineered. MIPS recently released the 2.6 version of MIPS eJTAG as a proposed standard, so hopefully there will be more support for that in the future. Flash numbers and EEPROMs we'll cover in a minute. These are the pinouts of a couple of JTAG ports. The JTAG port usually shows up as a set of pins on the circuit board, and on this router, could you put the camera up here again? On this router, it's basically 12 pins right down on the front edge. But it varies from manufacturer to manufacturer. The most important lines are usually, well, there's VCC and ground, which are just power and ground, and are usually used to power a device that plugs into the board. The device looks kind of like this. That's parallel port on one end, and then this header on the other end for connecting to that. Then there's NTRST there is test reset, and the N means that it's negative logic. In other words, it's true when the pin is low and false when it's high. That resets the test port of the chip. The other reset is NReset, which is reset the full system, and it can be used to automatically reboot the device that you're testing under software control if you want to start a second test or run a long series of automated tests.
Nice thing about JTAG ports being mostly standardized between a couple configurations is you have 4 input pins and 1 output pin. So if you're going to try to wiggle it to figure out your pin out, it's very difficult, unlike serial, where you can easily find your voltage and your ground, and then your TX and your RX pins. With this, you've got to get the 4 input pins correct to find the correct output pin, which is the response pin. So if it weren't a standard, it would be very difficult to figure it out on your own.
Don't skip yet. While they're not standardized terribly well among between manufacturers, usually one manufacturer will use the same JTAG pinout on all their boards. The router that we've been showing off and another router that I have both use MIPS processor cores, and their JTAG headers are both MIPS JTAG standard. The other lines here, TDI, TMS, TClock, and TDO, are the actual lines used for doing the JTAG communication. TDI is test data in and is a single wire serial line that's used to send data into the chip. TMS is test mode select, which is basically the enable for doing JTAG stuff and tells the test section of the chip to enable itself. T-clock is the clock signal, which is used for clocking the data in on TDI and out on TDO. So the way it's used is that data is sent into the chips, and then the resulting data is clocked back out. Because, if you'll skip to the next slide, this is a example layout of a set of just an arbitrary device that supports JTAG. The individual devices are daisy-chained, TDO to TDI, and they all share one T-clock line. So the data can be clocked into one device, and then if you want to reach the next device, you just keep clocking it, and it goes into that device, and then into the last device, and then finally starts coming back out on your TDO line. This is essentially a shift register, if anybody knows what that is, that incorporates every pin of every device in the circuit. This means you can set, under software control, the state of any device, or the state of any pin of any device in the circuit. So you can do what-if scenarios where you can say, well, what if all the data lines went high at once? You just clock in a whole bunch of ones until they're at those data lines and then see what happens. Another use is getting flash in or out. Since the flash chip will be connected to something that has JTAG pins, JTAG can be used to manipulate the pins that are connected to the flash chip, changing its address and address lines and then reading its data lines back out through the TDO port. Needless to say, this gets somewhat tedious. It's a single-bit serial protocol, and if you're trying to read several megs of flash over it, it can take a very long time, sometimes up to a half hour for reasonably sized flash chips.
There are open source tools available that will allow you to do manipulation via JTAG port. Depending on what device, there might be specific tools like routers have their own. I think there's one called Harry Dairy Made, yes, which is for debricking a router via JTAG port. And it's a very primitive implementation of the JTAG, but it does what it's intended to do.
EEPROMs are a technology for storing data on circuit boards that came well before Flash. You've probably seen an EEPROM chip if you opened up any older devices. They're usually kind of large, wide-bodied, and they usually have a clear window on the top that you can see the chip through. The reason for that is that the chip, it used to be that you would program this chip in a device called an EEPROM burner, and then take it out, put it into the device, test the device, and if there were any problems, you could then take it back out and erase it using ultraviolet light through the window on the top, and then put it back in. This is a hobbyist's homemade EEPROM reader and writer. They're useful if you have an older device, and in my case I had the magnetic card reader that I was talking about, to be able to dump all the code out of one of these EEPROMs. If you have an EEPROM that you can get the code out of, and you know the microcontroller that was used for it, you can use a program like IDA to reverse engineer the software, and from that modify or just even come to a basic understanding of the device. Do-it-yourself ones are available. This is kind of complicated, but if you look at these chips, they're all very basic logic chips. This is designed to be driven off of the parallel port of a standard PC using some Linux-based software, and would probably cost well under $100, possibly under $50 to put together. The thing is, EEPROMs are fast disappearing. They're an older technology, they're less easy to work with than Flash, and possibly less reliable. They also come in smaller sizes. Flash has kind of replaced them, and if you want to dump flash memory, you might do something like this. This device here is a digital camera made by a company called, I believe, Dakota Digital, that was sold as a disposable video camera at pharmacies in the United States. People didn't want to return it, though. They wanted to be able to buy one, use it to record videos, and then offload those videos onto their computer and record more videos instead of sending it back to the company to be processed and receiving the videos later and never getting their camera back. I mean, it's a simple money-saving thing. You don't want to buy a camera over and over and over again just to record short little videos.
And because you only rent the equipment, you're only paying $10 for a camera that might be worth 40 or 50 bucks.
So perhaps not in the
retail.
company's best interest, but certainly in the people's best interest. The device that's clipped onto it is a reader for XD or smart cards. XD cards, which are used in Olympus digital cameras, and smart media cards, which are used in some other companies' digital cameras, are basically a typical flash chip in a funny-shaped package. They have all the same data lines, all the same address lines, same power and grounding, and just this exact same signal set, just in a different package. This device is an adapter between a USB connection and the flash chip on this board. So the person can connect this up and then mount the flash chip as if it were a drive on their computer, use a program like DD or Copy to copy the data right off of there and into a file for later analysis. People did this and managed to reverse engineer out of it the unique keys that were used to, I believe it was either encrypt the data on the card or to authenticate to the camera before downloading the data out of it, and then could connect basically a USB port to these traces over here and get the data out themselves at home. The other possibility for getting the flash out is desoldering the flash chip, which is doable if you have hot air stuff, but is not a terribly easy process.
Once you get the firmware off and have it decompiled, you're going to have a big blob of assembly instructions, pre-initialized data for when the program starts off, and typical tasks it's going to do is it's going to do on the system on a chip initialization. It's going to initialize all its subsystems, set its memory registers, map the memory, and then it's going to clear the RAM, copy the initialized data into RAM, and start the main loop after creating the stack. So the first thing you want to look for is the reset vector of your chip, because that's your start point. Another nice thing is interrupt tables are usually well documented, and you may have 100 bytes per interrupt to have the interrupt inline, or most places will just branch off to a larger area of memory to do each interrupt routine. So you'll have like a serial interrupt, an SPI interrupt, basically interrupts for whatever timers and everything else on the board. And knowing that will tell you where to start, and once you start tracing through, you can start documenting this decompiled assembly code when you figure out what it does.
Once you have the software, it becomes a matter of software reverse engineering. You end up, like he says, tracing the interrupt vector to find your entry point and then decompiling the code. The difference is that you may have to learn the assembly language, the processor register layout, and the memory map of a whole new processor, because the chip isn't necessarily going to be x86 that the average program runs on. However, most manufacturers want it to be easy for you to learn their assembly language, their register maps, their memory maps, because they want you to use their chip. So if you get the data sheet for a chip, you can probably teach yourself the assembly language just based on that. The magnetic card writer that I dismantled and reverse engineered used the Motorola 6803 microcontroller. The Motorola 6803 microcontroller datasheet has a full table of what every single assembly language instruction does, memory map, where the interrupt reset vectors are, what the registers are, how the commands interact with the registers, everything you could want to know about programming the chip, and as a consequence, everything that you would want to know about taking the program out of the chip. What in the world is... It's a parade! Yay!
We'll just wait for a second for that to get by. It's a little distracting.
Well, that was really something. Once you have the data sheet, you can teach yourself the assembly language. And once you learn one assembly language, the majority of assembly languages are, to some degree, similar. You'll end up with, the typical push-pop instructions. In Motorola assembly language, interestingly enough, the pop instruction is not pop, it's pull. The opposite of pushing something onto the stack would obviously be pulling it off, not popping it off, which is an interesting piece of design decision on their part. Go ahead.
This slide also got screwed up a little bit. I'm not sure quite what happened.
We have a variety of people we'd like to thank. We'd like to thank the Hacker Foundation for putting together our trip over here. We'd like to thank the CCC for having us and the Angels for making our stay here easy. We'd like to thank all of you for coming to this presentation.
We're also thanking the Hacker Foundation, and they're trying to start the hackerspaces program in the US, which is encouraging people to group together, to work together on creating their own labs and pursuing their own projects. We wouldn't have been able to do this talk without collaborating and sharing knowledge, because he knows many things I don't know and vice versa. So if we weren't working together, there's no way either of us would have been able to put together this talk at the quality that we've made it. Here in Germany, you've got the CCC, which is very graciously hosting us and allowing us to speak. It's an excellent organization which encourages stuff like this. So thank you, and I guess now we're going to unplug the laptop and plug in the monitor for questions.
Yep.
Now, before you run off to your tent and fire up your soldering iron, there's a lot of time for questions. Are there any questions?
Just a very basic question about soldering. What's the right temperature for soldering? Because it always seems like a religious belief.
Well, on the topic of religious belief, I typically keep my soldering iron set at 666 degrees. That works well for me. I have yet to burn anything out.
For sensitive electronics, a range between 600 to almost up to 800, maybe 750 or so, can safely be used. You might want to go higher if you're desoldering, because that generally goes faster if you're using a wick to pull the solder out.
Yep. Yes, I believe
Fahrenheit.
it is.
Yes.
Yeah. Yep, Fahrenheit. Anyone else? Another thing, you can look up the data sheets not only on chips but on solder as well. There's low temperature solders, there are higher temperature solders. Basically, you can bring it down to trial and error. One thing that is good to have, though, is a temperature controlled iron. Very basic soldering irons are not temperature controlled. They just limit how much current passes through the device, which doesn't adequately regulate the temperature. It means that when you touch it to something that's large and can sink a lot of heat away, the iron temperature will plummet. And it may take a long time to heat the thing up. It may end up applying too much heat to the area under the iron before anything else is hot enough to solder to. If you have a temperature controlled iron, it will detect the drop in temperature caused by touching something like that and send more power. I use a temperature controlled iron. I grew up using a non-temperature controlled iron, and the difference is frankly fantastic.
Yeah, my soldering iron has two settings, 20 watts and 40 watts. I use 20 watts for applying most components to the board and 40 watts for desoldering from the board. But if I'm trying to solder something to a grounding plane that's going to diffuse a lot of heat, I have to kick it up to 40 watts or the solder just won't melt.
You talked about the reflow ovens at the beginning of your talk. Is there any do-it-yourself guide for or software to regulate the temperature? Because I was trying a bit and fucked up some PCBs.
There is a kit available from sparkfun.com, which is a hobbyist and electronic prototyping supply company that hooks up to toaster ovens and allows you to do some control via, I believe, the serial port of a computer, as well as having a temperature sensor in the circuit for feedback. That may give you better results than sitting there and watching it, but I'm not sure. I have very limited experience with this. I've done a little bit of reflow soldering using a hot air gun, which worked the first time and burned up the PCB the second time. So I'm not certain. There's that kit. Your mileage may vary.
I have a question. If I would like to start on microcontroller programming and I'd like to start with real basic things like flashing an LED or something, which chip would you recommend? Would you start, say, a PIC or an ARM or whatever?
AVR is a good one to start with. PICs are very difficult chips to program for. The only reason why they've become a de facto standard is because they're very, very cheap, and they've been used for so long that they keep using them. But when you're learning how to program for from a fresh start, I'd suggest the AVR, or if you can afford a prototype board for the PowerPC, a PowerPC 32-bit system on a chip is also a good starting point.
From my perspective, I have some experience with the AVR microcontrollers made by Atmel. This board is a development board for the ATmega 168 and the ATmega 8. It's called the Arduino. It's manufactured in Italy and has a open source programming environment and open source development toolchain based on AVR glibc, I believe. The development environment uses a language very much like C, but slightly more restricted because the chip is a slightly more restricted environment. There are a lot of very useful libraries available, including ones for doing things like writing to character-based LCD displays or controlling touch sensors. So with a very small amount of code, you can get something very impressive up and running. This board costs around $30 US and is available from, I believe, tinker.it. If it's not available there, they'll have links to suppliers. One of the suppliers in the US is sparkfun.com. The individual chips are available from any number of electronics distributors like Mouser, DigiKey, probably Conrad. They cost around $4 each, so that's American dollars. So even cheaper.
2-3 euros.
Yeah, exactly. Way to have a good exchange rate. And basically, you can flash the chips with the open source bootloader that goes on this, and then this hooks up via USB to a computer. So programming the chip is as simple as, whoops, not throwing your electronics everywhere. Programming the chip is as simple as hitting the reset button and then hitting a button in the programming environment to send the code to the chip, and then it starts running a couple seconds later. In fact, these boards used to come with an LED on them and pre-programmed with the blink the LED example.
Some of the more sophisticated bootloaders from the manufacturer will allow you to step through debug via serial port debugging. So it'll be running code through the bootloader and stepping through by almost virtualizing the application running, but really the bootloader is the primary program running and communicating via serial port. So if you don't want to get something like BDM or JTAG to do step-through debugging, look at the what functionality the manufacturer-provided bootloader might provide in that arena.
I'm going to reiterate that I highly recommend that. I built a project using that was a model of a 30-story apartment building with about 5 apartments per floor. Every single apartment could be turned on or off with a remote control. The whole thing was, I believe, a total of like 12K of code when it was all compiled, and it used 2 of those chips, one in the remote and one in the base of the tower. It was very easy to do on-the-fly modifications, repairs, get the thing running, and I learned a lot from that project as well about that microcontroller. I'm very attached to it.
Yeah, just a suggestion. If you want to try soldering and programming microcontrollers, there's the lochraster.org page, which has the blinking light board on there, a microcontroller controlled LED light. With it, I think it's an Atmel Mega 8. It's quite famous in the club, so you might give it a try.
Mm-hmm. And the Atmel Mega 8 is also programmable with that setup, so you can go either way. Another thing that's interesting, Mitch, I've forgotten his last name, the man who was in the Hack Center.
He doesn't use his last name. He's speaking later tonight, and it's just Mitch. He's very easy to spot. He's got purple hair on one side, and he has the brain programming stuff with light and sound. Those use very simple microcontrollers, and I think he has kits that he's selling for building your own.
Those kits are a very simple development board for that microcontroller. They have a serial port that you can reprogram the controller over. So some people have been reprogramming their brainwave goggles, and if you get one of those kits, I believe it's between $40 and $50 American, I think. You have a development board for that kind of kit. And I believe the software is all free open source.
Excuse me. There's this. You said that there are some guys here who are who brought a reflow oven with them. Who are they?
The Viennese camp, I believe it's MetaLab, has a toaster oven that they've been using to reflow parts for a LED display that they're building.
Oh, and another question. After, like, I didn't really hear you say this, but like you said that there's after a workshop of some kind, or where you could.
Were we doing a workshop?
I don't remember what you said actually. It was something like that.
Mitch was doing a workshop in the Hack Center on building the brainwave goggles.
Yeah, we have some tools that we've kept down there. I've left my soldering iron and helping hands, but I haven't actually been in the Hack Center helping out. It's been
yeah.
pretty full.
That's what you said. You brought some tools, was it?
I have some tools with me. I have not. Well, I did a little bit of a thing at the Hack Center where I gave away a few kits for a logic analyzer and a simple logic probe. If you're looking to get the microcontroller kit that was used in the brainwave goggles, the man you want to see is Mitch, who is doing a Hacking Your Brain presentation.
I think it's later today.
Yeah, later today, I believe, in this very same room. Does that answer the question adequately? I'm not sure that I...
Yeah.
Others?
More questions?
Nope. All right, well, thank you very much.
Yeah, thank you for having us. It's been great talking.